Stop hoping the model formats correctly. Validate every response and return a safe fallback. You get unpredictable model output when you need structured data. That breaks downstream code and surprises users. Today you will learn a small, reliable pattern that gives you parseable model outputs and a safe fallback when things go wrong. You will be able to extract a structure, check it, repair it, and never crash production over a single malformed reply. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Models will hallucinate, trim, or wrap JSON in prose. That matters when your pipeline expects a neat object. The practical problem is not model quality alone. It is robustness. Success looks like a predictable object arriving for every call, or a clear fallback path you control. Most teams fix this by validating and falling back, not by trusting luck. The intuitive idea is 3 parts. First, parse the noisy text for the nearest JSON, like we fish out the useful bits. Second, validate that the fields you need are present and correctly typed. Third, repair what you can and return a tested fallback if you cannot. This approach trades a little code for a lot of reliability. We will build a tiny pipeline that extracts JSON from model text, checks required fields, scores alternatives, repairs bad types, and returns a safe fallback if needed. First, we pull the structured payload from messy text and try to parse it. Now, we will extract and parse the JSON text. This snippet extracts and parses a JSON object from noisy LLM text. This snippet looks for the first coherent JSON-like block inside the model reply, trims surrounding prose, and runs a tolerant parser to convert it to a native Python mapping. It starts by locating brace boundaries or triple markers, and then calls a safe parse routine that captures parsing errors rather than throwing them. The key lines show the extraction step, the tolerant parser call, and the error capture. If the parser fails, this snippet returns a descriptive error object that the next stage can inspect. Adjusting the aggressiveness of the extraction will change how greedy you are at grabbing partial JSON from the text. Next, we will check the structure for required keys and correct types. This snippet validates required fields and types against a minimal schema. This snippet defines a minimal schema of required names and expected basic types, then walks the parsed object to confirm presence and type. It reports missing keys and type mismatches as structured diagnostics rather than raising an exception. The core lines build the schema, iterate over schema entries, and append issues to a problems list. If every required check passes, the snippet returns a clean validation result. Tuning the schema to be stricter will reduce downstream ambiguity, but increase fallbacks. Looser rules accept more variation, but risk subtle bugs. Next, we will score multiple parse candidates and pick the best one. This snippet scores candidates and selects the more complete structured output. This snippet takes multiple parsed variants, for example, the first JSON block and a later block, or alternative parsing strategies, then scores each candidate by completeness and type correctness. The scoring logic weights presence of required keys more than optional ones and penalizes type errors. The code enumerates candidates, computes a numeric score, and picks the highest scoring candidate for further processing. If scores tie, it prefers the candidate with fewer type repairs. You can change the weights to prefer fewer repairs or prefer preserving more original fields. Next, we will repel types and constrain values for stable downstream logic. This snippet repairs types and constrains fields to stabilize downstream logic. This snippet inspects problematic fields and applies deterministic repairs, like converting numeric strings to numbers, trimming extra whitespace, and bounding numeric ranges. It also enforces constraints, such as allowed enum values or minimum lengths, to prevent surprises. The core lines list repair rules, Apply each rule and track what changed so you can log repairs. If a field cannot be safely repaired, the snippet marks it as unrecoverable in the diagnostics. Tuning the repair rules decides how aggressive the system is at mutating model output. Next, we will wrap the full flow and return a safe fallback when validation fails. This snippet wraps parse, validate presence, and returns a safe fallback. This snippet composes the previous steps into a single call: extract, validate, score candidates, repair, and finally return either a validated object or a predefined safe fallback structure. The code DAF builds a consistent return shape with a success flag, the validated object when available, and diagnostics when not. The fallback is a conservative object your downstream code knows how to handle. The final lines decide when to accept a repaired result and when to return the fallback, and they also emit a compact log entry for monitoring. Choosing a more conservative acceptance threshold increases fallback frequency, but removes subtle errors. This toy pipeline maps neatly to production. Replace the toy parser with a streaming-tolerant JSON reader. Wire diagnostics into your observability stack, and run the same validation rules on live traffic to measure failure rates. Recap what it is: a triple pattern of parse, validate, fallback that forces predictable outputs. When to use it: anytime an LLM is asked for structured data that feeds other code. One caveat: aggressive repairs hide model mistakes, so log and monitor repairs. Next step: scale and evaluate this exact approach on a larger sample of model replies. Measure the fallback rate and add timing and accuracy checks so you can tune thresholds. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.